Today we're going to be going over, we never got to the last lecture, we're going to start pointers last lecture. We're doing memory and pointers. So the joke here is assembly is a very powerful tool. If you want to write a really fast piece of code, there's nothing faster in the world than assembly. That's the machine language. C, you got to reinvent the wheel, so they're making a gun here, but you got to hit the ball with a hammer. C++, if you guys notice the knife sticking backwards, that's kind of the joke with C++, right? C++ is a very powerful language, but when it goes wrong, you're going to stab yourself or you're going to blow your whole hand off. It's not a forgiving language. And then Python's just this automated machine that you just click the on button and it throws pistols that shoot each other. Okay, so before we start, I had a curiosity. So grab your clickers, fill that one out. Okay, so looks like most of you guys are using the VM. We've got some Xcode, we've got some Visual Studio, and 13 others. All right, here's on that one. All right, I'm gonna move on. This is my course material. All right, converse with your neighbors. What do you guys think on this one? We'll come back to this question too. All right, I'm going to stow this one for now. That was interesting results though. I'm not going to show them to you yet. So let's start diving into what's going on here. Remember I said C++ is a good teaching tool because you need to know how the computer works. If you know how the computer works, you can do C++. So let's start into how computers work. In each computer, there's a little hamster and a little wheel. Now this computer's got 4 hamsters in it, quad core. And it's hyper-threaded, so theoretically it's like 8 hamsters. I'm serious. There's no hamsters. All right, so you guys are all familiar with the concept of computer memory, right? It's the stuff that you're always running out of. It's the stuff that if you don't have enough of, your computer just goes unbelievably slowly. Computer memory, as a program sees it, is a single array. It's one giant array with byte. So it's an array of bytes. A byte is 8 bits. Now, it's not, when you put something into this array, it just exists contiguously in this array. This isn't like a 2D array. It's just a big giant array of stuff. And each index into the array is given an address. Just like when you access an array in C++, you can start at index 0. Main memory starts the exact same way. It actually starts at index 0. Now index 0 is reserved. We'll find out why later. You will never, ever, ever have a piece of code loaded at index 0. And it goes all the way up to the maximum value of whatever your operating system is. So if you're on a 32-bit system, it goes up to the value of 2 to the 32, which is in hex, OX, and then 8 Fs. Okay, so when your program gets loaded into memory, by the way, memory stores everything. Your program, your data, strings, inputs, outputs, everything, including what's being drawn on the screen. That's actually stored in memory as well. So when your program gets loaded, it's given a big chunk for program data. And we'll look later, program data is actually split into 2 distinct pieces. For now, think of it as one piece, and then your actual program. And your program, remember, it's a whole bunch of assembly. And assembly is just ones and zeros. Assembly language, as the words you guys are thinking of, is just a way to represent those ones and zeros. It maps directly to ones and zeros, something the computer can understand. So let's say your program's running right here. This green line right here is the next CPU instruction. By the way, a CPU just goes through instructions one after another, forever. It'll just keep going down the list, executing one instruction after another. It'll never stop. So this instruction is an add operation. We're going to be adding 2 integers together. And the way this works at the CPU level is you have an add instruction, and then you tell it where in memory these 2 integers exist. Now, those of you who are paying very close attention will notice that these numbers are not off by 1. They're off by 4. So an int is 4 bytes. So you've got, here's your first integer, 4 pieces, 4 bytes. Here's your second integer. So from here to here is actually 4. So just keep that in mind, that's why you see offsets of 4. So the CPU gets this instruction, and now it says, oh crap, I need to go get something out of memory. So it looks in memory, finds these 2 spots in memory. Think of these just like array indexes. It's a giant, giant, giant array. And these hex values here are just numbers. When we actually look at some C++ code, I'm actually going to represent them as numbers, because I think looking at pointers in hex is what causes people brain damage, because it's not a difficult concept. I think it's just seeing, OX, FA, 8, 7 that just makes everyone's brain shut off. This is just a giant array, just like in C++. You access it just like any other array. So it's going to grab the two values that it sees in memory. I've zoomed in here. So each one of these represents, let's see, these represent 4 bytes, because I've offset them all by 4. So this is 4 bytes continuous, and then these are another 4 bytes, then another 4 bytes, another 4 bytes, et cetera, et cetera. The CPU loads these two numbers out of main memory, and inside the CPU, you don't need to worry too much about what it does, but it stores these two numbers somewhere temporary called registers, and then it actually adds them together. It does this add operation right here. And it gets the result 66, stores that in another register. Now, there's an actual store instruction. It doesn't look, assembly doesn't look like this, by the way. This is pseudo assembly. And I say store the result of these adds at this address right here, which just happens to be right below these two integers that I just added together. Yep?
Maybe misunderstanding, but are they labeled incorrectly with the 8 and 0, where you're storing it being where it's issued?
Oh, yes, that was labeled incorrectly. You are right. That should be B0, right there. Either that or the arrows are off, I'm not sure which. But yeah, you're correct. So this address right here should match that address right there. We've got some typos going on. Yeah, there's the store address. Good eyes. Yep. And then once that, so this was the instruction we were executing beforehand. Now the CPU automatically goes on to the next instruction. Your program doesn't need to say, please go on to the next instruction when it's done. It just goes forever, keep going down the instructions. And here's the 3 little pieces of data right here that we touched. So, these are pointers. They're in hex. Oh my gosh. Hang in there. So, now let's look at some code. If you guys are paying attention, the claim that I just made is that this foo right here exists in memory somewhere, and it has an address. Actually, let's see if you guys can answer it. Let's see if we get different results on this one first. I'm curious. Here, revote on this one. And pay close attention to what I just showed you guys about data and what instructions do. And I promise there are not hamsters in your computer, unless you've done something wrong. Or right, yeah. When I was actually Googling for hamster computer, there's people that made hamster cages that are a computer. Like the computer's up top, up above, and they got a hamster wheel in there. Look funny. All right, so here's what you guys are showing for results. About half D, about half B. So some of you guys think that it can look at the format of data in memory. Now remember, main memory is a big giant array of ones and zeros. It's not organized in any way, shape, or form. I could have a string sitting in memory that's exactly 4 characters long, and you would be unable to distinguish it from an integer. Because those same 4 bytes also represent some number. And maybe that number was being used for something else. Maybe those 4 bytes and the next 4 bytes are actually part of a long, a 64-bit word. So you can't just look at memory and figure out what it is. Apparently I forgot to stop it because everyone's jumping ship. So what ends up happening is the CPU actually runs, your program says, add integers here and here. And then the CPU goes and it grabs 4 bytes, and it grabs 4 bytes, and adds them together. If you had the exact same memory, and you said add floats, it's going to grab 4 bytes of data, treat them as floats, add them together, whatever their ones and zeros may be, you're going to get some result, and then it's going to store it back. So it all depends on what instruction you tell the CPU to run. Yep?
In C++, that we mark the int float, isn't that the purpose of declaring the type?
Right, so that's a good question. His question was, in C++, don't you mark the int in the float? So let's look at this. If I were to do something like this, remember this needs to be compiled down into a machine language. Or even let's say foo equals plus equals 1. So we're trying to add 1 to foo. How does the compiler know what foo is? It has no idea what foo is. It doesn't know what instruction to run on the CPU. Is it adding a float? Is it adding an int? Is it adding a long? It doesn't know. So we put int, whoops, we don't put int there. we put int here to tell the compiler that when it generates an instruction to add those together, I'm talking about integers.
So it tells the compiler.
It tells the compiler, yeah. And then the compiler is going to go through and generate CPU instructions that it needs to add those ints together. So, in C++, everything in C++, every piece of data has an address. And actually, you'll find out this includes things like string literals. If I type open quote, close quote, and then some literal string in there, that actually exists in data too. It gets loaded into data. It doesn't move around. It's always going to be in the same spot. It gets loaded in with the actual program, but it's in memory. So that means that logically, if everything has an address in C++, and C++ is all about the pointers, that we have some way to get the address of any chunk of memory. Any variable in C++. So now the fun starts. This is the first new operator you guys are going to learn right now. This is the address of operator. You can stick this in front of a variable and find out where it lives in memory. This is super useful. So let's look at some of this in C++. If I have foo, I can see out the value of foo, and of course I get 42. So very unexciting. What I could do is put an ampersand in front of foo. What that tells the compiler is, and this is a compiler thing, by the way. This is the compiler doing this for you. I don't want the value of foo. I want ampersand where foo lives in memory. And what it's going to give back to me is an address. So if I run this, I get some ugly hex value. That is just a number. So from now on, I'm going to represent, for the next while, I'm going to represent pointers as longs, just as numbers, so that it causes less brain damage. So if it was a giant array in memory, foo would exist at this obscenely large index into the array. And the reason that it's obscenely large is because your program doesn't get loaded into spot 0, so it's going to just start off with some huge value. Now if I did another int, and then I spit out the address of bar and print these two, you'll notice these two values are off by 4, because these two things live right next to each other in memory. And that has to do with the way that a function is created and the way that a function runs, but local variables will always be right next to each other in memory. And each one's an int, so they're, of course, 4 apart. If I did this, if I turn these into 64-bit numbers, they would be 8 apart. Right? Yes. Okay, so let's go back to ints. Okay, let's do one more thing. Now, before we actually get into real pointers, I'm going to do some pseudo pointers. I'm going to store the address of foo. So the ampersand in front of foo gets the address of foo. It's in hex, and C++ actually, we'll see later, it's got special types for pointers. So I'm just going to trick C++ and say, please treat it as a number. Now, anytime later in my program, I can actually look at the address of foo. And if I just spit out the address of foo, look at here, hopefully it should be the exact same thing as what was printed above, and as it is. So we can store an address as just an integer in our program. And we could pass that integer around and let someone else use that chunk of memory. All right, converse with your neighbors. Okay, good. So this is what we got for results. The majority of you think B. It's the address of bar. That is true. I'm trying to trick you here by setting the value of bar to be the address of foo, but we don't actually care about the value of bar. When we say ampersand bar, we're saying where does bar live in memory? I don't care what it is. I don't even care what type it is. Just give me the beginning of where it lives in memory. It's the only thing I'm asking it. So if I say ampersand bar every single time, I'm just asking what is the address of bar. Now bar itself happens to have the address of foo in it, which could be useful, could be not useful, but D is the correct answer. Okay, so we just saw you can store a pointer. If you treat them as integers, you can just store it as a long, right? Here's the problem. What does this function take in? It's a pointer to something, but a pointer to what? You have no idea. And this isn't just a problem with, you as a coder. You could theoretically write a C++ program that just uses longs for all of its pointers. It would just be unmanageable. You wouldn't be able to use it. It would just be a total disaster. But you could. So C++ introduced a concept of a pointer. And someone was asking on Friday what that little star was. You guys see a little star after float? That's a pointer. What you've declared here is it's a pointer to a float. So when you see stars, when you guys start doing this, by the way, this is going to be really difficult. And it's going to take you like 10 minutes to write one line of C++ code with pointers and stuff in it, because this is a new way of thinking. But when you see a pointer, step back, and you may even want to write this down in English, and decode what that is. So you can have as many stars as you want, but read them right to left, and replace each star with the words a pointer to, until you get back to the basic type, and then it's just a float. So this is a pointer to a pointer to a float. And you can have a pointer to a pointer to a pointer to a pointer to a pointer. You can go as many times as you want until it just gets totally absurd. And there is actually uses where you want to have a float star star. So another way to think about this is, if you have a pointer to a pointer to a float, the pointer to a pointer to a float itself is called myCrazyType. So this is myCrazyType. Now remember, names are just a way, if you say int foo, that's just a way of naming some memory address in a more useful way. It exists in memory. You could actually say, instead of myCrazyType, you could say OXFFAC, whatever it is. And you get the exact same thing. That's where it lives in memory. We've just chosen to name them so that it's easy for the programmer. So the entire type is this whole thing. And what it is a pointer to another pointer that happens to point to a float. So this last thing right here is a float. It's not named. We can't get at it by naming. But we do have a way to get at it because we now have 2 pointers. Questions on that? No? Does this all make sense to everyone? Or does it make so little sense that nobody has any questions to ask? Yep.
So where is the name myCrazyType stored?
It's not stored. The compiler uses it to figure out what you're talking about. Think of it like an alias. I don't feel like remembering OX7F whatever, whatever, whatever every time I want to reference my foo integer. So I just alias it as foo. And then the compiler is going to go through and figure out what I'm talking about. And it's actually going to completely strip out the name altogether. The final compiled assembly has the word foo in it absolutely nowhere. So it doesn't exist in the final binary. It's just for programmer convenience. Good question. Yep.
So how does the pointer point to that other place? Does it just have the address of the other place?
Yeah, exactly. And let's see. I think I have. No. You'll see later. Hold off on that question for just 1 second, because I'm going to demonstrate what this looks like in memory later on. But yeah, exactly. Okay, so converse with your neighbors. All right, a couple more seconds.
Hi.
Yep.
Just out of curiosity, are variable names usually camel cases in C++?
Sorry, say that one more.
Are variable names usually camel cases in C++, or is it just...
Variable names, local variable names, are almost always start in their camel case, so they start in a lowercase letter, and then each new word is uppercase. So in Python, the convention is to separate words with an underscore. In C++, you just capitalize the first letter of each word with the exception of the first word. Okay. So you guys pretty overwhelmingly have decided D here. Int star star. So if we read int star star in English, you get it's a pointer to an integer. Guys, quiet. Unless you guys have questions, then feel free to ask. Yep.
it could also be B, because you're dealing with the pointer to an int is bar, or is it?
No, that's not quite correct. So what's my next slide? Do I go over any of this? No. Okay, so his question was, it could theoretically be B because it itself is a pointer to an int. But there's a flaw in what you just said, because it's a pointer to what type? A pointer to an int. So what you just said in a complete sentence is, it's a pointer to an int. So always read your types completely, never just chop off the stars. It's important to keep them in there. So D is the correct answer. It's an int star star. A pointer to a pointer, and the final thing at the end is an int. Okay, so what then is Baz put in different terms? Correct. So remember we had a pointer to a float, but yes. We had a pointer to a float, but the middle pointer and the float were not named. We didn't have access to them because we hadn't named them anything. This is a case where you've got a pointer to an int, where everything is named. The integer itself, the final thing all the way off to the right, is called foo, and it is itself an integer. Then the middle pointer is called bar, and the last pointer, the one that points to the pointer that points to the end, is called baz. All right, get out of here, 18 people. Yep.
The reason you want to do this is because that gives you the ability to use bar or int star as a bar, like somewhere else unrelated to Baz. Now you can have a bunch of bars, square food, and a bunch of bar, which is
Oh, why would you want to chain them together like that?
we couldn't just like, why don't you just have int Baz equals ampersand food?
Yeah, so his question was, why do this whole double pointer thing? Why not just have a single pointer bar that points to foo? And the answer is, in this specific case, where it's a pointer to an integer, there's very few cases where it's useful. I bet I could find some case where it's useful, but it's very useless. And you guys, I know you love me because I always show you useless C++ code, but I gotta get the point across. Yep.
So the third line is pointing to an integer, but the value it's assigned is a long, isn't it? The address of bar?
Oh, okay, so are you asking if the pointer itself is a long?
Yes.
Yes, so the pointer itself is actually 64 bits wide because Mac OS is 64-bit. So when Mac OS refers to any spot in memory, it does it with 64-bit alignment. So it's always going to jump around by 64 bits. I could have actually forced, so while the integer itself may be 32 bits, the pointers that point to it are actually probably twice that size. Which, that's just kind of like, and you actually don't need to worry about it quite yet. Yep.
So ampersand foo is the address of foo, right?
Yep.
Is that the same as the pointer?
Yeah, when you store it, it's kind of called a pointer because you're storing an address somewhere. When you actually store it in a local variable to use.
Okay, then I don't understand why you need the asterisk next to int, because it's already a pointer. Why do you need to say it's a pointer?
This right here, or the third line?
The second line you say int asterisk bar. Why do you need the asterisk instead of just saying this is the pointer?
Because, so if we go back to these slides here, where we were storing everything as a long, we could do that. We could just make, it has to be a long, not just an int, because pointers are 8 bytes, but you could use a long for everything. And then it would be a long foo, and then a long bar that just happens to have the address of foo in it, and then a long baz that just happens to have the address of bar in it. And that's fine to do. But the problem is you've now lost concept with, if I just give you baz, you don't know what it is. Because I've just handed you a long. You don't know if it's a pointer to a pointer, you don't know if it's a pointer to a float or a pointer to an object. You've lost concept of what it is. So instead, they've made up this convention where you put a star after the type that it's pointing to. And this actually tells the compiler explicitly, this is a pointer, treat it like a pointer, and it'll enforce a whole bunch of really cool safety checks for you so that you don't do something totally crazy and pretend like it's an integer. It'll enforce safety checks, and it pretends like it's, It stores the address there, but it's actually part of the language saying this is a pointer, not just a regular number.
Okay, so the set is basically reinforces the pointer. If that was, do you also need it because it's an int?
Oh, you're saying, could this be something else? Like, could you have int foo and then a long star?
Yeah.
No, because, and that's part of the safety thing here. If I just give you Baz, its declared type is a pointer to an int. So what I just said at the very last part of that sentence is important. I said it's a pointer to another pointer, and then this one points to an integer. So if I told you, well, this is now a pointer to a long, then C++ will be fine with that, and it'll treat it like it's a long, but it's not a long. So you're just going to get corrupted data that's just going to go totally insane. Now, if you try to say long star star Baz equals ampersand bar, it'll throw a compiler warning, a compiler error. It won't let you compile it. But you could coerce C++ into doing that. All right, other questions? Yep.
Could we have, if we only change the first and the third int to long, for example, do we also need to change the middle one, or? Okay.
Yep. Yeah, every single type needs to match up here. Because it's a pointer to whatever the final data type is. So whatever the final data type is, every pointer that refers to it, or some child of it, some other pointer to it, has to be the same type. Okay, so, probably should have shown you guys this slide earlier. I forgot what slide we have here. So this is the exact same code. Here's our int foo. It exists somewhere in memory. Here's our star int bar, our pointer to an int bar. It actually exists in memory somewhere, and it just happens to have the address of wherever foo lives in memory in its slot. And then the exact same thing with Baz, except it points to bar. So this kind of answers what he asked quite a while ago. Let's look at what this actually looks like in memory. So we start off with the exact same code here. This is our memory layout, program data, assembly. This is what memory looks like after this code is done running. Now, the foo, bar, and Baz here don't exist in memory. I've just put them in there so that you can reference them. So we've got 4 bytes right here that holds an integer, and it's got the value 42 in it. And it exists at this address right there. 6F, 9A, 89B, 8, I don't really care what the address is. It lives at this address. This is where bar lives. Bar itself stores a value. It happens to store the value of this address. Now these are just bytes. This is just some number. But because C++ has this concept of pointers, when it generates code for you, it's going to treat this number like an address. And this is all 32-bit. You guys see this is 4-byte offset here? So these are 32-bit pointers. Yeah.
Why do we have to worry about the 0x?
That's just a way of declaring hex. Traditionally, you put OX in front of a hex value, just to say this is hex and not something else. It could be octal, it could be some multiple of hex, 32 or something. It's just tradition. Yep.
Are these pointers manipulatable like variables?
Yes. So his question was, are these pointers manipulatable like variables? You can actually, here, let's do this in code. Watch this. Let's do foo, and then let's do int bar, oops, int star bar equals ampersand foo. So now bar stores the address of foo in it, right? Watch what I can do. Bar plus equals 1. This doesn't plus equals 1 to 42. This plus equals 1 to the address that's stored in bar. This is, of course, invalid code now. So, if I printed out bar before I did that, and then I printed out bar after I did that, the pointer itself just changed. Now, what you've just done here is destroy your pointer. Because now, if I try to use that pointer, pretending that it points to an int, it doesn't anymore. It's now pointing to 1 byte off, which means you're just going to get some garbage data sitting at the end of the last byte of your integer. But you can do it, and it's actually super useful. We'll find out why. Yeah?
They look at it should be like 4, not 1.
Oh, that's because it knows it's an int. Okay, so it's trying to be a little clever here. So what it's done here is it knows that an int is 4 bytes, and it's offset it by 4. There's also something else you can do in C++. There's size of, and this is super useful.
showed this earlier.
Oh, it's size of all the different data types?
Yeah.
So you can see int is 4. Now what's the size of int star? This should be 8. 8. So a pointer to an integer is twice the size of an integer. That could be a problem. All right, back to slides. So the next question is, I've made all these pointers going to random places in memory. Whoop-de-doo. How on earth is that useful? I've got a pointer that points to an integer somewhere in memory. Can I do anything with that integer? Or am I just forever left with this number that points to something in memory that I can't access? Kind of the sarcasm should give that answer away. So this is where we come into the dereference operator. Now, the dereference operator is really frustrating to me because C++ uses the ampersand 3 different ways that mean 3 completely different things.
Order,
What's the fourth?
ampersand, ampersand, bitwise ampersand.
No, that's Python. Ampersand is Python. You mean power?
No, and Boolean.
Oh, I'm talking about stars. Oh, I see what you're saying. Yeah. The ampersand for, yeah. The ampersands are also used a dozen different ways.
Oh, yeah.
I mix those two up all the time when I speak, by the way. If I say ampersand and it sounds like I'm talking about a star, it probably means I'm talking about a star. So I'm talking about stars here. So this first one here, you're multiplying 2 floats, 2 ints together. That's one meaning of it. This next type you guys have seen right here. It's how you declare a pointer to something. You can have as many of those as you want. Interestingly, before we get too far ahead, int star bar is the exact same thing as int space star bar. And nobody sticks with any convention on this. I see some code that uses int space star bar, and some code that uses this. This is also valid. So pay close attention. What's going to get confusing is if you see this, what does this look like on this slide? Looks like that. But it's not that, so be careful. That's going to get confusing. So then we've got this third type here, which is the dereference operator, which we'll look at how to use in a bit. But there's 3 different meanings of this exact same damn symbol. It's really, really frustrating. It's going to get super confusing.
Shut.
So, yes, but calm down. All right. So before we get into this question, let's actually go over how to use some of this stuff. If it's not on how to use the dereference operator, is there any other questions? Yep. Probably. It's freaking C++. Yeah. I mean, there are places where C++ cares about spacing. Like, if I took that space out right there, it can't distinguish between the int and the main. It doesn't know where the space is. But yeah, you could have no space as well. If any of you guys write code with no space in it, I'm going to come find you. I personally like the int star because I can read the entire data type all at once. But I see code all the time with it the other way. Both types are valid. Okay, let's look at actually how to use the dereference operator. So don't confuse this with the dereference operator. That's not what it is. Let's see out foo. Let's see out bar. Now this is the pointer bar. So far I should have 42 and then the address of where 42, foo, lives in memory, which we do. Now, let's say that I don't have access to foo, but I want to get whatever foo was. That's where the dereference operator comes in. I put a star in front of bar, with bar already being a pointer. You can only do this if bar itself is a pointer. So what this tells C++ is I'm not actually interested anymore in bar itself. I want the thing that bar points to. So if I run this, I'll get, voila, 42. It's called a dereference. Yeah.
It works with numbers, or do you have characters stored data?
It works with anything. Not only is it just, not only is it the built-in types, int, longs, char, all those, it works with objects. This is how you pass objects around in C++ too. You actually never want to pass an object directly, because C++ has to go in and make a copy of the entire object for you. You just pass a tiny little pointer to this giant object, and then someone else can just use that pointer. Yeah?
You don't point it to a private variable, star type variable, you get around it in private.
Yeah, that's one of the ways to get around it. One of the ways to get around it is actually just to get the address. So this is your object, right? This is your public data. This is your private data. The question, by the way, was, can you use this to get around the public-private thing? Public data, private data. All you do is get the address of the object, and then just add on to that address, like we did earlier, where we just wrecked our pointer. Just add on to that address however many off it is in memory. And it's predictable how many off it is in memory. It will always be the exact same. And then voila, you've got access to all the private data. I mean, it's effortless to get around. It's not a security thing.
Hey, that's the basis of so many hacks right there. Okay, and viruses and things like that. That's why, well, you can tell Alec gets excited about pointers in a way that I don't. And I suspect a lot of you are longing for Python again, but I'll let Alec continue.
Yeah, I love getting down to the metal and watching how the machine works. I actually started with a lot of electrical stuff. Yeah?
So is that how a keylogger?
No. Keyloggers do something totally different, unfortunately. Yeah, there's a whole class here called ethical hacking, taught by John Black. It's an awesome, awesome class. But you can't do any of that stuff until you know, like, down at the assembly level how the computer works. That's where all the hacking takes place. You guys, we are totally out of time. We got more material, so I'll see you guys Wednesday.